We often think of space as right, a void.
The ultimate nothingness.
Exactly. But what if that emptiness isn't empty? What if it's actually like an ocean of energy, always moving, even at the coldest possible temperatures?
You're talking about the 0-point energy field.
That's the one. And the whole idea just flips our usual picture of nothing, completely upside down.
It really does. And what's amazing is this isn't just science fiction. It actually comes straight out of the core principles of quantum physics.
Right.
It makes you totally rethink what nothing even means. It suggests there's this, well, hidden potential everywhere.
Which is exactly what we're diving into today. We've got some really interesting material here called WAIU, and our mission basically is to unpack this whole 0-point energy thing.
Sounds good.
We want to get a handle on what it is, look at the history, how scientists figured it out, the science it's based on.
And maybe even touch on some of the wilder ideas connected to it.
Yeah, exactly. Consciousness, maybe. Yeah. And definitely the big question. Can we actually use this energy, even though it sounds, well, really hard?
It's a huge challenge, no doubt.
Think of it like an adventure, right? From the tiniest quantum jitters to maybe, just maybe, a totally different future.
And stepping back, you see, this isn't just some abstract science thing. It has these huge implications for how we understand reality itself, from subatomic particles all the way up to the whole cosmos.
Okay, let's get right into it then. What is the 0-point energy field? The name itself, 0-point energy. Sounds like it shouldn't exist. Energy at zero.
Well, that contradiction is actually the whole point. It takes you straight into quantum mechanics. See, even at absolute zero temperature.
Where everything should just stop, classically speaking.
Exactly. But quantum fields, they never really stop. They keep fluctuating. Imagine like an ocean surface that looks totally calm. But underneath, there are always these tiny currents, little movements. That underlying activity, that's the 0-point energy field.
Okay, so an ocean of energy, even in what looks like empty space.
Wow. And these fluctuations, they cause something even weirder, don't they? Virtual particles.
Precisely. These constant jitters in the quantum fields. They actually cause pairs of particles and antiparticles, like electrons and positrons, or these things called virtual photons, to just pop into existence.
Out of nothing.
Out of the field's energy, yeah. For incredibly short times, we're talking less than, like, a quadrillionth of a trillionth of a second.
Whoa.
And then, poof, they annihilate each other, giving the energy right back. We call them virtual because we can't really see them directly, normally.
But they have real effects.
Oh, yes. Very real, measurable consequences.
Faster than you can blink. Way faster. So what's the theory behind this constant popping in and out? Why does it happen?
That takes us to a cornerstone of quantum mechanics. Heisenberg's uncertainty principle. Essentially, it says you can't know certain pairs of things about a quantum particle perfectly at the same time. Like its exact position and its exact momentum.
There's always some fuzziness. Exactly. Because of that built-in uncertainty, even at absolute zero, particles can't be perfectly still in one exact spot. They have to have some minimum energy, some jiggle. And that minimum energy shows up as these 0-point fluctuations and these virtual particles flickering in and out.
So the universe is fundamentally jittery. It can't quite settle down. That's wild.
Yeah.
Okay, but this idea, it didn't just appear fully formed, did it? How did scientists even start thinking about this stuff?
Well, the very first seeds were planted way back, actually, with the start of quantum theory itself. Max Planck, back in 1900, showed energy comes in little packets, right? Not continuous.
Quanta.
Then Niels Bohr, in 1913, with his atom model, he suggested that even at absolute zero, the electrons and hydrogen still had some minimal motion.
So even then, a hint that zero wasn't truly zero.
A very early hint, yeah. Things weren't totally static, even at the lowest possible energy.
Okay, so hints in the early models. But when did it become this idea of a field everywhere?
The next really big step was Heisenberg's uncertainty principle in 1925, which gave the theoretical why for this leftover energy. But the first really solid experimental hint, that came much later. Hendrik Casimir, 1948.
The Casimir effect.
Yeah.
That's the one with the two metal plates super close together in a vacuum.
That's it.
And they actually pull towards each other because of the 0-point energy.
That's exactly right. Casimir figured that if you put two conductive plates really, really close, the 0-point fluctuations between the plates get restricted. Only certain wavelengths can fit.
Okay.
But on the outside of the plates, all the fluctuations are still there, pushing in. So you get this tiny imbalance, a net pressure pushing the plates together.
And you can measure that push.
You can. It took a while, but in 1996, it was measured precisely, confirmed. Really strong proof that the vacuum isn't empty.
Wow. Empty space literally pushes things around. That must have been huge.
It fundamentally changes how you think about space, yeah? Empty space exerts a force. Think about that.
Definitely a turning point. Now, Einstein came up earlier. How does he connect to all this?
Well, thinking bigger picture, cosmology. Einstein put that cosmological constant into his general relativity equations, remember? He wanted a static universe.
His biggest blunder, he called it later.
He did, especially after we found out the universe is expanding. But here's the twist. Modern cosmology suggests this constant might actually be real. It could be linked to some kind of energy inherent in space itself.
Like dark energy.
Exactly, like dark energy. And dark energy might possibly be related to this zero-point energy field. So funny enough, his blunder might have accidentally pointed right at vacuum energy.
Incredible how that works sometimes. What about Nikola Tesla? He was mentioned too, talking about energy from cosmic radiation. How does that fit?
Tesla's ideas, looking back now, seem almost prescient. Early 20th century, he's talking about Earth absorbing energy, tapping into some cosmic source.
Which sounded maybe a bit out there at the time.
Definitely. The science then couldn't really explain it. But from our view now, knowing about the zero-point field, this idea of a huge untapped energy reservoir everywhere, his intuition seems remarkably spot on.
Almost spooky. Thinking about something a century before science really caught up. And Andrei Sakharov, induced gravity. What's that about?
Oh, that was radical. Sakharov, in the 60s, suggested maybe gravity isn't fundamental, maybe it's an emergent thing.
Emergent, like it arises from something deeper.
Exactly. He proposed it might arise from the quantum fluctuations of the zero-point field itself, like a large-scale effect of all that tiny quantum fizzing.
Whoa.
It hinted at this deep link between quantum mechanics and gravity, suggesting the zero-point field might be key to a unified theory of physics.
So gravity itself might be a side effect of the vacuum energy. Okay, my brain hurts a little. And quantum electrodynamics, QED, that sounds like where the serious math comes in.
It absolutely is. QED, developed by Feynman, Schwinger, Tominaga, they won the Nobel Prize for it, is incredibly precise. It describes how light and matter interact. And it describes the vacuum not as empty, but filled with this fluctuating electromagnetic field, filled with those virtual photons we talked about.
Right.
And these aren't just math tricks. Their interactions explain real things, like the Casimir effect, and also something called the Lamb shift.
Lamb shift.
Tiny, tiny shifts in the energy levels of electrons in atoms. They happen because the electrons are interacting with the zero-point electromagnetic field. QED predicts it perfectly. It's one of the most successful theories we have.
So we've gone from early hints to experiments to super precise math. The zero-point field seems pretty solid.
Yeah.
But there's that huge elephant in the room, right? The energy density. The vacuum catastrophe.
Ah, yes. You've landed on one of the biggest, most baffling mysteries in physics.
Tell me about it.
Okay, so the quantum field theory calculations, they suggest the energy packed into the zero-point field should be absolutely enormous, colossal.
Oh, enormous.
Like a cubic centimeter of vacuum about the size of a sugar cube should theoretically contain more energy than, well, more than ITER, that massive fusion reactor puts out in a whole year.
That's insane.
It is. But then we look at the universe, we see how it's expanding, we try to measure the energy density driving that expansion, the dark energy, which we think is related, and the number we measure is tiny. It's about 120 orders of magnitude smaller than the theoretical prediction.
120 orders of magnitude. That's not just wrong, that's fundamentally broken somewhere, isn't it?
That's exactly the problem. A factor of 10 to the power of 120? It's the worst prediction in the history of physics, basically. It screams that we're missing something huge.
It's like predicting Mount Everest and finding a grain of sand.
A very accurate analogy. It's the vacuum catastrophe or the cosmological constant problem. Are our theories of quantum fields or gravity just wrong? Or is there some mechanism canceling almost all of it out that we just don't know about?
A massive cancellation. It's a huge puzzle. It really makes you think maybe the energy we see is just the tiniest ripple on this immense hidden ocean.
That's a very good way to put it.
Now, the material also mentions some early attempts, maybe less conventional ones, to actually tap this energy. People like Murray, Bowman, Searle,
Yes, those names often come up in this context, mostly in the mid to late 20th century. They claimed they'd built devices that could pull energy from the surroundings, cosmic energy, things like that.
Like More's box or Searle's generator.
Right, or Bowman's Testotica machine.
Hmm.
They claimed anomalous energy output, but the big issue was always the lack of rigorous proof. No solid scientific documentation, no independent verification, no theory that really fit with known physics.
So they didn't really get accepted by mainstream science.
No, not really. They remain sort of historical curiosities, you could say. Interesting but not scientifically validated examples of zero-point energy extraction.
Right, so maybe more imagination than solid science there. What about more recent, more grounded work? Harold Puthoff's name came up, vacuum engineering.
Yes. Hal Puthoff has done more systematic theoretical work. He's explored ideas around vacuum engineering. The concept is maybe you could design special materials or structures, maybe at the nanoscale, that create specific asymmetries in the vacuum field. And maybe those asymmetries could allow a directional flow, potentially letting you extract useful energy.
So trying to manipulate the vacuum itself with carefully designed tech.
That's the idea. It's still theoretical and debated, but it represents a more physics-based approach than some of the earlier claims.
And it seems this whole line of thinking has branched out even further, hasn't it? Into biology, consciousness.
That's where it gets really fascinating and also, frankly, quite controversial. Lynn McTaggart's book, The Field, for instance, explores this idea.
What's the core idea?
That maybe the zero-point field isn't just fundamental to physics, but maybe also to life processes and even consciousness itself.
Well,
some people even try to connect it to ancient concepts, like prana in yogic traditions or ki in Chinese medicine, suggesting maybe science and ancient wisdom are pointing at the same underlying reality.
So it's not just about new energy sources anymore. It might be about the nature of life itself. That's a huge leap. But it brings us back to the core problem, right?
Yeah.
If this energy is everywhere, why is it so hard to grab? Thermodynamics seems to be the big wall.
That is the central debate, yes. The standard view, based on the second law of thermodynamics, is you can't get net energy out of something that's in thermal equilibrium, like a uniform field.
Like trying to power a boat using the heat already in the ocean water.
Exactly. You need a difference, a gradient. But some argue the zero-point field might not be perfectly uniform or in equilibrium at all scales. And maybe weird quantum effects like non-locality or tunneling could offer loopholes.
So is it a smooth, unusable energy bath? Or does it have exploitable ripples or non-equilibrium aspects? That's the big question.
That's pretty much it. We're right at the edge of what we know. The existence of the energy is pretty well accepted now, with good evidence.
Yeah.
But can we actually harness it efficiently? That's still very much an open question. But just exploring it is changing how we think about the vacuum, energy, matter, everything, really.
Okay, let's really dig into the quantum physics here. Zero-point energy is the most fundamental energy state, even at absolute zero. Why? What stops everything just grinding to a complete halt?
It comes back to that fundamental fuzziness in quantum mechanics, Heisenberg's uncertainty principle again.
Right.
Quantum fields just can't be perfectly still and have zero energy. There's always this inherent minimum level of activity, this constant trembling, even in a perfect vacuum. That minimum energy is the zero-point energy. It's built into the fabric of the quantum vacuum.
So even if you took out all matter, all radiation, this background hum of quantum activity would still be there.
Exactly. Quantum field theory tells us every fundamental particle has an underlying field permeating space. The vacuum is the lowest energy state of all those fields combined.
But lowest doesn't mean zero.
Correct. Lowest means non-zero. That residual energy is the zero-point energy.
And these constant tremblings are what spawn the virtual particles.
Precisely. The field fluctuations momentarily borrow energy to create particle-antiparticle pairs, which then vanish, returning the energy. It's happening constantly, everywhere. And it causes real effects, like the Casimir force pushing those pleats together.
The Casimir effect really seems key, doesn't it? Solid experimental proof. And you mentioned the theoretical energy density is just astronomical. Remind us how big and why that's such a headache.
Right, the calculations suggest this density is immense, that sugar cube-sized bit of vacuum. Theoretically, more energy than a giant fusion reactor puts out in a year.
Which leads to the vacuum catastrophe.
Yes, because if there was that much energy, according to Einstein's general relativity, it should have a huge gravitational effect. It should curve space-time massively.
But it doesn't seem to.
Not even close. The observed energy density driving the universe's expansion dark energy is, again, about 120 orders of magnitude smaller. It's this massive gulf between theory and observation that tells us our understanding is seriously incomplete.
It's like the universe knows a secret consolation trick we haven't figured out yet. Okay, quantum electrodynamics, QED. How does that specific theory handle the zero-point field?
QED is our super precise theory of how electrons and photons interact. It treats the electromagnetic field as quantized made of photons. But crucially, even in the vacuum, with no real photons, QED says the field is constantly fluctuating. It's a sea of virtual photons popping in and out.
And these virtual photons have real consequences.
Absolutely. They interact with real electrons, causing things like the Lamb shift, that tiny energy level difference in atoms we couldn't explain before QED. The incredible accuracy of QED gives us huge confidence that this fluctuating vacuum picture is fundamentally correct.
So the math works beautifully. The predictions match experiments. Virtual particles are effectively real in their influence. How does this loop back to cosmology and Einstein's cosmological constant problem?
Well, as we said, Einstein put the constant in for a static universe, then regretted it. But now we know the expansion is accelerating, driven by dark energy.
Which might be related to vacuum energy.
That's a leading idea. Maybe dark energy is the cosmological constant, a manifestation of the vacuum's inherent energy, the zero-point energy. The giant problem, of course, is still that 120 orders of magnitude difference between theory and observation. So, the connection's plausible, maybe even likely, but the numbers are wildly off.
It's like we have the right concept, but the wrong scale entirely. It's amazing how interconnected it all is, though. Quantum fields, cosmology, and then there's the Unruh effect. That sounds even stranger.
Oh, the Unruh effect is deeply weird and wonderful. It connects acceleration and temperature in a vacuum.
How so?
It says if you accelerate through what a stationary observer sees as empty, zero-temperature vacuum, you, the accelerating observer, would actually perceive it as being warm, filled with a bath of particles.
Seriously. Just by accelerating.
Yes. It means the very concepts of vacuum and particles aren't absolute. They depend on the observer's motion. It ties zero-point energy directly into relativity and suggests maybe particles are just excitations of this underlying field.
So accelerating stirs up the vacuum, making it seem hot and like stuff. Wow. And what about quantum foam? That sounds like we're getting down to the absolute smallest scales.
We are. Down at the Planck length, incredibly tiny, 1035 meters, some quantum gravity theories suggest space-time isn't smooth. It's chaotic, turbulent, like foam.
Driven by quantum fluctuation.
Exactly. This quantum foam could be the ultimate manifestation of zero-point energy, where energy and space-time geometry are tangled together, constantly fluctuating. It's where quantum mechanics and gravity must merge, though we don't fully understand how yet.
The deeper we look, the weirder and more active reality seems.
Yeah.
Now, besides the Casimir effect, are there other experiments confirming zero-point energy's influence?
Definitely. The Casimir effect was the first big direct one, but other things point to it too. Quantum tunneling particles getting through barriers they shouldn't is influenced by vacuum fluctuations.
Oh, yeah.
The behavior of superconducting Josephson junctions, they're sensitive to the zero-point field. Even the way atoms emit light, the spectral lines are slightly broadened because of interactions with the field.
So its fingerprints are all over quantum phenomena.
Pretty much. And in 2015, there was a big step. Scientists directly measured the quantum fluctuations in the field using sophisticated optics, so it's not just inferred anymore.
Direct measurement, that's significant.
Yeah.
And it affects materials too, like graphene.
Yes, especially in these new 2D materials like graphene, just a single layer of carbon atoms. The electrons in those systems are super sensitive to their electromagnetic environment, and the zero-point field plays a big role in their properties. It's driving a lot of research in quantum materials.
Amazing how this background energy affects stuff we can actually make and study. What about squeezed vacuum states? Sounds like manipulating the field itself.
That's exactly what it is. In quantum optics, they've figured out how to squeeze the vacuum. They can reduce the quantum fluctuations in one aspect of the light field, say its amplitude, below the normal vacuum level. But the catch is you have to increase the fluctuations in another aspect, like its phase, because of the uncertainty principle.
So you can trade uncertainty between different properties.
Sort of, yeah. Being able to create and control these squeezed states is more proof the field is real and shows we can manipulate it subtly. It's important for things like quantum sensing and communication.
Like learning to sculpt this quantum ocean, just a tiny bit. But despite all this evidence and understanding, getting usable energy out, still huge hurdles, right?
Yeah.
Vacuum catastrophe. Second law of thermodynamics.
Those are the big two, yes. The 120 orders of magnitude problem shows our theory is incomplete, making it hard to design an extraction mechanism. And the second law seems to forbid getting net energy from a uniform field in equilibrium.
But people like Hal Puthoff suggested ways around that, creating quantum asymmetries.
Right. His idea is about clever engineering, maybe design materials or structures at the nanoscale that create a non-equilibrium situation, a way to make the zero-point energy flow directionally, like creating a temperature difference for a heat engine.
So tricking the vacuum into giving up energy by making it non-uniform locally.
That's the hope. The challenge is figuring out how to actually create that kind of quantum gradient or directed flow effectively.
A huge challenge. And what about Timothy Boyer's work? Stochastic electrodynamics.
Boyer's model gives zero-point energy an even more fundamental role. He suggests it's not just background noise, it's essential for stability. He argues that the constant interaction, the buffeting of electrons and atoms by the zero-point field, is what stops them from spiraling into the nucleus, which classical physics predicts they should do.
So the vacuum energy actively holds atoms together.
In his model, yes. It emphasizes that zero-point energy isn't passive. It's actively maintaining the structure of matter.
That's a profound thought. Okay, let's shift gears a bit to the really speculative side, the connection to consciousness. That really challenges the idea that mind is just brain chemistry, doesn't it?
It absolutely does. It pushes against that traditional mind-matter separation. The core idea here is maybe consciousness isn't just confined to our neurons. Maybe it's connected to these deeper universal fields like the zero-point field.
And the Oort-Shor theory by Penrose and Hameroff is a big one here, involving microtubules in neurons.
Yes, that's probably the most well-known. Sir Roger Penrose, the physicist, and Stuart Hameroff, the anesthesiologist. They propose consciousness arises from quantum processes inside microtubules, these protein structures in brain cells.
Quantum processes in the brain.
Their Orker's theory, orchestrated objective reduction, suggests quantum coherence can be maintained in these microtubules, maybe interacting with the zero-point field. And when these quantum states collapse in an orchestrated way,
that's a moment of consciousness.
That's their hypothesis. They even suggest microtubules might act like quantum computers. It's radical and highly debated, but connects consciousness directly to quantum physics and potentially the zero-point field.
So thoughts and feelings might be quantum events, influenced by the vacuum energy. Wild. What about David Bohm's implicate order?
Bohm took an even broader view. He saw our perceived reality, the explicate order, as just an unfolding of a deeper, interconnected reality, the implicate order.
Like a hologram.
Exactly. And he suggested the zero-point field could be the physical manifestation of this implicate order, this vast sea of potential from which both matter and consciousness emerge, like vortices in a stream all being part of the same water flow.
A very holistic picture. The zero-point field as the source of everything matter and mind. Does that connect with Carl Pribram's holographic brain idea?
It resonates strongly, yes. Pribram suggested memories might be stored holographically, distributed across neural networks. Bohm's physics and Pribram's neuroscience seem to fit together, with the zero-point field possibly being the quantum medium supporting this holographic processing in the brain.
Amazing how these different fields start to converge. And we're seeing quantum effects in biology beyond the brain too, right?
Increasingly so. Photosynthesis is incredibly efficient due to quantum effects. Bird navigation using Earth's magnetic field seems to involve quantum mechanics. Even our sense of smell. Hameroff argues microtubules are structured perfectly to support these quantum states, potentially making them the carriers of consciousness.
So life might be quantum-powered in ways we're just starting to grasp, which leads to the idea of non-local consciousness. Could the zero-point field be the connection?
That's the speculation. Quantum entanglement shows connections faster than light. If consciousness is quantum, maybe it's non-local too. The zero-point field, being everywhere, is proposed as the potential medium for these non-local conscious connections or information transfer. Highly speculative, but it offers ways to think about things that are hard to explain classically.
Like maybe our minds aren't just stuck inside our skulls. What about Lynn McTaggart's work on intention, influencing things physically?
McTaggart explores if focused intention can affect physical systems, potentially through the zero-point field acting as a medium. She points to things like the Global Consciousness Project looking at random number generators during big world events.
Does the data show anything?
The results are debated, controversial, but the idea is provocative. Maybe there's a shared conscious field interacting with the physical world via the zero-point field.
Intention shaping reality through the vacuum energy is a huge paradigm shift. And the parallels with ancient ideas like
Yes, some researchers speculate Qi might relate to zero-point energy, and the meridians in acupuncture might be pathways that conduct or interact with specific frequencies of it. There's some preliminary research looking at electrical changes at acupuncture points, but it needs much more work.
so ancient wisdom might have tapped into something fundamental science is now rediscovering. What about measuring fields during meditation?
People like Elmer and Alice Green did measure unusual electromagnetic fields around people in deep meditation. It suggests focused consciousness can interact measurably with energy fields. Maybe meditation is a way to tune into the zero-point field, leading to those experiences of cosmic consciousness.
Like we have a built-in way to connect with this field. There were other, even more out-there ideas mentioned too. McFadden.
Jack Sarfati suggests consciousness actively influences quantum events, like wave function collapse, via the zero-point field. John Joe McFadden's CE-MI theory proposes consciousness is an electromagnetic field generated by neurons, and this field interacts with the background zero-point field to create coherence, maybe linked to gamma brainwaves.
So consciousness isn't just watching, it's participating, maybe even creating coherence via the zero-point field. And remote viewing, like the Stargate project.
Extremely controversial. That project looked into claims of perceiving distant information without normal senses. The results are heavily debated, not widely accepted scientifically. But if such things were real, some speculate non-local connection via the zero-point field could be an explanation. You have to be cautious here, maintain rigor.
Definitely need skepticism. Yeah. And Ken Wilber's integral theory trying to pull it all together. Zero-point energy as a subtle energy level.
Wilber tries to integrate different levels of reality, physical, mental, spiritual. He suggests the zero-point field might correspond to a subtle energy realm, bridging matter and consciousness, echoing ideas like prana or chakras.
So this field might be the missing link between the physical world and our inner experience. Huge implications for health and healing too, right?
Absolutely. If mind and this field are linked, things like the placebo effect, energy healing, intention healing, they might have a real physical basis in this interaction. Experiments suggesting consciousness can influence biological systems remotely point in this direction too.
Our thoughts and intentions having real power. And finally, Wheeler's participatory universe. Observation creating reality.
John Wheeler's idea takes it to the cosmic scale. Experiments like the delayed choice suggest observing a particle now can influence its past. It implies consciousness isn't just watching the universe, it's participating in bringing quantum reality into being.
Wow.
Again, very philosophical, but it suggests a deep, intimate dance between consciousness and the cosmos, potentially mediated by the zero-point field. It's truly frontier stuff, blurring science and deeper questions about reality.
Absolutely breathtaking. Okay, let's ground ourselves again. Practical applications. Harnessing this energy. Where are we really at with actual technology?
Right, back to practicalities. And the honest truth is, we face enormous challenges turning the theory into usable power. But there are interesting research paths being explored.
Okay, like what? Are there working devices based on the Casimir effect?
Yes, tiny ones. Proof of concept devices. Labs at Caltech, Delft University, they've made microscopic MEMS devices. They use that Casimir force between tiny plates to generate minuscule amounts of power.
How minuscule?
Microwatts, really, really small. It's more about showing, yes, you can get energy out this way, it works, but the efficiency is incredibly low. Nowhere near practical yet, but it's a start. It proves the principle.
A tiny first step. What about quantum rectification? Trying to channel the random fluctuations.
That's another approach, trying to use clever materials or structures to turn the random quantum jiggles into a directed electrical current. There was a report in 2019 using graphene and boron nitride, claiming some very preliminary success.
Again, tiny amounts of energy.
Negligible, really. More proof of principle that you can maybe influence these fluctuations, but not a power source yet.
Okay, and the solid-state devices that supposedly borrow energy? Those sound the most speculative.
They are. Lots of claims, patents. Very little solid, independently verified proof accepted by mainstream science. The idea is maybe special materials, superconductors, or quantum dots could somehow interact with the zero-point field to release energy.
Any examples?
There was a claim from a DOE-affiliated lab about a thin film device extracting electrons via tunneling at room temp, but it hasn't been widely replicated or validated. So, intriguing concept, but the evidence is currently weak.
Right, needs that independent verification. What about exploring systems far from equilibrium? Maybe thermodynamics doesn't apply strictly there.
That's more theoretical modeling, mainly in Russia and France. Exploring if systems driven way out of equilibrium, think complex nonlinear oscillators might temporarily behave strangely, maybe seeming to violate the second law, perhaps drawing energy from their surroundings, which could include the zero-point field.
But still theoretical.
Highly theoretical at this point. No demonstrated devices that sustainably violate thermodynamics this way.
So practically, we're still at the very beginning, facing huge hurdles. Remind us of the biggest ones again.
Okay, number one. The theoretical debate, does tapping a uniform field violate the second law? Mainstream says yes. Number two, the vacuum catastrophe that 120 orders of magnitude gap shows we don't fully understand the fundamentals, making it hard to design anything.
Right.
Number three, technical difficulty. We need incredible precision, manipulating things at the nanoscale, often with super pure materials. Very hard to do reliably, let alone mass produce. Number four, efficiency. Current prototypes are way below 1% efficient, useless for practical power. And number five, reproducibility. Too many claims haven't been independently verified, leading to skepticism.
Sounds like we need breakthroughs in both basic science and advanced engineering. Are there any really cutting-edge research areas that offer some hope?
There are a few exciting directions. One is quantum vacuum plasma. Researchers are exploring if super strong electromagnetic fields near the Schwinger limit could actually excite the vacuum, maybe polarizing it enough to pull out real particles and energy.
Using massive lasers to zap the vacuum.
Something like that. Facilities like ELINP are trying to test these extreme predictions. Another area is the dynamic Casimir effect.
How's that different from the regular one?
Instead of static plates, you rapidly move or vibrate the boundaries of a cavity, like mirrors. Theory suggests this rapid change could shake real photons loose from the virtual ones in the zero-point field.
Has that been seen?
There's some experimental evidence using superconducting circuits suggesting it might work, generating real photons this way. That's encouraging. It shows dynamic manipulation is possible.
So moving boundaries might be key. What about new materials like topological insulators?
Those are really interesting. They insulate on the inside but conduct electricity perfectly on their surfaces. How electrons behave at these surfaces might offer new ways to interact with the zero-point field. Some research, like from the Chinese Academy of Sciences, hints at unusual energy effects at these boundaries.
Exotic materials with unique quantum interfaces, and looking to biology for ideas.
Definitely. Photosynthesis is almost 100% efficient in converting light energy in some bacteria. How do they do it? Probably sophisticated quantum tricks. Studying these natural systems could give us design clues for artificial energy harvesting, maybe even tapping the zero-point field.
Nature's had billions of years of R&D, right? And what about a more pragmatic approach, just using zero-point effects to improve existing tech, not replace energy sources entirely?
That seems much more near-term, yes. Instead of limitless free energy tomorrow, maybe use our understanding to make better solar cells by designing nanostructures that tweak the local zero-point field, or improve catalysts, boost existing tech, rather than aiming only for the Holy Grail. That could be impactful much sooner.
A more realistic path forward, perhaps. Okay, let's imagine a breakthrough does happen. What kind of applications could we see?
Oh, the potential is revolutionary. Even modest energy extraction could mean distributed power everywhere. Think sensors for the Internet of Things, medical implants like pacemakers that never need new batteries.
A lifetime pacemaker.
Wow. Remote monitoring systems. For space exploration, it's huge power independent of the sun for deep space probes, long missions, maybe auxiliary power.
Who else?
Quantum information is already using vacuum fluctuations for random number generation and cryptography. Better control could lead to more powerful quantum tech. Material science could see entirely new materials, room temp superconductors maybe, perfect insulators, smart materials.
And propulsion.
That's more speculative, but the idea of quantum vacuum propulsion getting thrust directly from interacting with the zero-point field, no propellant needed, is out there. NASA's even done some early controversial tests. It would totally change space travel.
The possibilities are staggering. But a technology this disruptive, huge social and ethical questions too, surely.
Enormous. Energy access could be democratized, shifting geopolitics, reducing resource wars. Energy might become a public good.
A massive change.
Environmentally, it could solve climate change zero emissions. But we'd need to watch for unforeseen environmental effects from large-scale devices messing with the vacuum economically, total restructuring, fossil fuels decline, new industries rise, an energy abundance scenario, and regulating it globally, a massive challenge for governments.
A double-edged sword, potentially. Given all this, what's the best way forward for research?
Balance is key. Rigorous theory combined with carefully designed, independently verifiable experiments. Interdisciplinary collaboration is crucial. Physics, materials science, engineering, biology. Setting realistic, staged goals, incremental progress is better than waiting for a miracle. Open verification is paramount for trust. And responsible innovation, thinking about the impacts from day one.
Sounds like a wise path for exploring such a powerful frontier. Okay, wrapping up this deep dive, what are the absolute key takeaways about zero-point energy?
First, empty space isn't empty. It's full of this fundamental zero-point energy that's backed by solid science like the Casimir effect. Second, understanding it has been a fascinating journey involving physics giants. Third, the theoretical energy is mind-bogglingly huge, but tapping it faces immense challenges, the vacuum catastrophe, thermodynamics. Fourth, it connects to deep mysteries like consciousness and the nature of reality itself. And finally, while limitless free energy is still distant, research is active, and we might see benefits sooner by using its effects to boost current tech.
It really sits at an amazing crossroads: physics, tech, philosophy. A fantastic deep dive into something that could genuinely change everything. So here's a final thought to leave you with. If the vacuum is this incredibly dense ocean of energy, what does that imply about the real matter and energy we see? Could our familiar reality just be the surface ripples, the very tip of this vast, energetic iceberg? Something to really chew on.
Definitely food for thought.
We really encourage you to explore more, maybe look into Tesla's early ideas, the details of the Casimir effect, or those mind-bending theories linking quantum physics and consciousness. This journey of discovery is really just getting started. Thank you so much for joining us on this deep dive.